All right, so we're going to start in on a new chapter here, chapter 11, on substitution versus elimination. Very sad day for everybody here, starting our last chapter of this semester. I know, super depressing, coming to a close here, okay? We're actually still going to be focusing on these alkyl halides. All right. Last chapter, we talked about alkyl halides as a functional group, introduced them, and we learned a bunch of reactions. Those reactions largely focused on creating alkyl halides. So now we're going to talk about using alkyl halides as substrates. And it turns out that there are these two reactions that are going to be in competition with one another. All right, the first is what's called a substitution reaction. All right, a substitution reaction is where we substitute that halogen functional group for another functional group, so swapping out this bromine for something else. What we're going to find is these are nucleophilic substitution reactions. So for right now, I'm just going to use Nu with a lone pair and a negative charge to represent my generic nucleophile. All right, and what we're going to see is that these alkyl halides react with nucleophiles, and we swap out that halogen functional group for whatever that nucleophile is. All right, so these are a substitution reaction. We're going to substitute our halogen for a nucleophile. All right, and these reactions are in competition with what are called elimination reactions. And an elimination reaction is where we take our alkyl halide, we get rid of that halogen again, but now we're not substituting it out. We're going to form a carbon-carbon double bond here. So we're converting our alkyl halide into what? An alkene. All right, in an elimination reaction, let's look carefully at our product side here. What new bond are we creating? That carbon-carbon pi bond. And if we look on our reactant side here, what bonds are we going to need to break in order to create that new bond? Our carbon-halogen bond, and what else? Let's fill in our implied hydrogens here. How many implied hydrogens do I have on this carbon? 3. And how many implied hydrogens do I have on this carbon? Only 2. All right, so we're going to need to remove a hydrogen from a neighboring carbon in order to do our elimination reaction. We have a special name for those hydrogen acceptors, for those proton acceptors. Those are what we call bases. And so in our elimination reaction, we treat our alkyl halide with a proton acceptor, with a base, and we get this elimination reaction. Okay, so alkyl halides, they have these two competing reactions that occur. Either substitution when we react it with a nucleophile, or elimination when we react it with a base. And the reason why this is going to be sort of complicated, like I said, they're in competition with one another, is there are plenty of molecules, like a hydroxide ion, for example, that are both good nucleophiles and good bases, right? So if we treat an alkyl halide with one of these molecules that's a little bit of both, we're going to get a mixture of these two reactions. All right, so what we're going to do is we're breaking this chapter into 3 lectures here. One where we focus only on the substitution reactions. The other where we're going to focus only on the elimination reaction. And then the last one where we'll focus on the competition of the two of them together. All right, so today's discussion is going to focus only on the substitution portion of these reactions here, swapping out our alkyl halide, swapping out our halogen specifically for a nucleophile. All right, now, one of the reasons why these reactions work is because if we look at our alkyl halide here, we know that it plays the role of what in a chemical reaction here with our nucleophile? What role is the alkyl halide playing? The electrophile. And specifically, what is the electrophilic site of this molecule? That carbon that is bonded to our halogen here. This is my electrophilic site. Why is it electrophilic site? Because we have this polar bond where that halogen is stealing a bunch of electron density. All right, and importantly, that carbon can accept electrons because what role does that halogen play? A leaving group. All right, so let's talk about leaving group-ness here for a second. All right, if we want to rank from our worst leaving group to our best leaving group, all right, what we're going to see is that it is inversely related to how basic that group is. So our worst leaving groups are our best bases, and our best leaving groups are our worst bases. All right, these two are inversely related to one another. All right, let's just kind of note that. Our good leaving groups are bad bases. All right, so since we're talking about alkyl halides here, let's go ahead and just rank all of our different halogens, right? Chlorine, iodine, fluorine, and bromine. All right. According to our Fario rules, if we go to our periodic table here, wherever that is. All right, so fluoride, chloride, bromide, or iodide, right? That's the order that they appear here. So which one of these is going to be the worst base, and which one's the best base? So when our sizes here, which one was the stronger acid, hydrofluoric acid or hydroiodic acid? Hydroiodic acid with that large, very stable anion here, which means that if that's the strongest acid, this is the weakest base. Fluoride is the strongest base. All right, so if we're going to rank our alkyl halides here in terms of how good their leaving groups are, oh, I was in the wrong place. That's confusing. All right, which one of these is going to be the best leaving group? Holy hell, what did we just say was the worst base? The worst base, the iodide. So then which one of these is going to have the best leaving group on there? If Good leaving groups are bad bases. I believe in y'all. We can do this. All right, the iodide. There we go. Worst bases, best leaving groups. And it trends in order of size here, right? That was our Fario rule, where those larger atoms were more stable holding those negative charges than those smaller atoms. All right, so in fact, when we talk about our alkyl halides, we often leave out alkyl fluorides from that discussion because they're just really not very good leaving groups. So they will not react the same. We sort of will put these three together, but it's worth noting here that your alkyl iodides are even more reactive than alkyl bromides, are more reactive than alkyl chlorides. And we're going to kind of leave off these alkyl fluorides altogether in our discussion of these substitution versus elimination reactions. All right. Another one that we can put here that has a terrible leaving group is an alcohol. Alcohols, that leaving group would be a hydroxide ion. What do we know about hydroxide ions? Are they good bases? Yeah, so they're terrible leaving groups, those alcohol leaving groups. All right, if you want to kick off an alcohol, there's sort of some tricks that we can use. All right, and one of them is so this is how we're going to convert an alcohol to a good leaving group. All right, one of the ways that we could do it is by converting it first to an alkyl halide. We talked about that last chapter, but there's another one that we sort of lump in this same discussion here. All right, and this is what's using what's called tosyl chloride. You'll see this abbreviated as TSCl. All right, importantly, the structure of that molecule let me actually just draw it out after we react here. Creates essentially a sulfate group on that halogen. There's some complicated, there's kind of like a benzene ring going on back here. I don't really care about drawing out the whole structure. But importantly, this sulfates being absolute terrible bases, right? Sulfuric acid is a strong acid. This thing over here is a great leaving group. All right, and we have a way to abbreviate this. We usually don't draw out the whole structure. Instead, we just say OTS, where that TS is from our tosyl chloride. All right, and whereas alcohols are absolute terrible leaving groups, as soon as we add in that tosyl chloride, we get a very good leaving group here. Not technically an alkyl halide, but since it's such a good leaving group, it undergoes these similar reactions. So we basically just want to recognize if we see this OTS or we see an alcohol treated with tosyl chloride, all we've done is create a molecule like an alkyl halide that has a really good leaving group built on there. Okay. Cool. All right, so before we sort of go on to talk about these specific substitution reactions, we're going to look a lot at these energy diagrams today. All right, so I just kind of want to remind, we've actually already reviewed this, so I'm going to go pretty quick here. But just to remind everybody what I'm talking about, this is where we make this plot of how energy changes during the course of a chemical reaction, what we would call reaction progress or reaction coordinates. All right, and our reactions will start at a certain energy level and end at a certain energy level. This is the energy of my reactants. This is the energy of my products. All right, and then what happens in the middle of these graphs? What does it look like? Yeah, it's got this little bell or hump shape to it. All right, and importantly, there are two pieces of information that we get from these curves. One, just by looking at the endpoints here, where we're starting in energy versus where we're going in energy. In this particular example, my products are lower energy than my reactants. So what is that in terms of chemistry? Is that good or bad? Do we like low energy or not? Yeah, low energy is good, right? So this would be a reaction that would be favorable from what we'd call a thermodynamic standpoint. All right, specifically in this chapter, we're going to be looking at free energy diagrams. So the difference between these here, where we start and where we end, corresponds to the delta G of our reaction. All right, remember with delta G, a negative delta G is good, meaning that this reaction will proceed in the forward direction, or what we would call an exergonic reaction. All right, my products are lower energy than my reactants. So that's what we get information by just looking at our two endpoints here. Or we could look in the middle here. This is what we call what? From where we're starting with our reactants to the top of this hump here. This is our activation energy. And what does our activation energy tell us about our reaction? Boom, there's the key there is speed, how fast the reaction occurs. So what we would call in fancy chemical speak, in chemistry speak, the kinetics of a reaction. But yes, how fast or slow a reaction is. All right, so one part of this graph, rather the two endpoints here, tells us information about our delta G. Remember, delta G is proportional to your equilibrium constant, tells you whether or not your reaction is going to go forward or backwards. The other piece of information we get by looking at the middle here is how fast or slow that reaction is. All right, two different things. You can have a reaction that is very slow but very favorable towards the products. And you can have fast reactions that are not so favorable. So two different pieces of information that we get here. Let's just make sure that we're clear. Energy, reaction coordinates. Okay. Let's say that I have two reactions here. They're both going to start and end at the same place. All right. The difference being what's going on in the middle here. So if I'm comparing these two reactions, which one's more favorable from a thermodynamic standpoint? From my endpoints here, red, blue, are they the same? They're the same. What about from a kinetic standpoint here? Which one of these is going to be the faster reaction? The blue, this is my fast reaction. The red represents my slow reaction because it's got that higher activation energy barrier. All right, and how do I overcome an activation energy barrier? Let's say that we're over here at our reactant energy. All right, if we're going to jump over this activation energy barrier, how do we do it? Where does that energy come from? Catalyst would be a good way to lower an activation energy barrier, but sometimes you can't have a catalyst. Like, you got to be lucky that you can catalyze a reaction. And there's a big study as to how we catalyze reactions, but not all reactions have a catalyst. Yeah, there's one way that all reactions get energy in order to jump over this barrier. If we were sitting at absolute zero, this dot would just be stuck right there. It doesn't have any energy to jump over anything. When we apply heat, that's when we start getting a little bit of energy to jump over these humps here. So yes, how do we overcome? All right, let's just make this clear. How do we overcome an activation energy barrier? All right, the answer is heat. That's why many of our reactions that we carry out in the lab, we have to carry out at an elevated temperature so that they have enough energy to jump over and get to the product side. So according to that logic here, which one of these am I going to need more heat for? My slow reaction or my fast reaction? My slow. So your fast reactions you can get away with at low temperatures. Your slow reactions are when you're going to need to apply heat in order to overcome that activation energy barrier. All right, and then lastly, I said that this one was an exergonic reaction. I want everybody to take a second and draw me the free energy diagram for an endergonic reaction. All right, what would that look like? Endergonic meaning it's a positive delta G. All right, so I'm going to draw in my reactant energy level over here on the left. When I draw in my product energy level over here on the right, where does it have to go? Higher than my reactants, right? So endergonic, meaning your products are higher energy than reactants. All right, and then we need our little hump in the middle here. Something like that would be an endergonic reaction. Okay? So now, let's think about our reactions in the reverse direction. All right, here's our marble. We're over here on our reactant side. We got enough energy to jump over this activation energy barrier. But what if it wants to go the other way? Remember back in Chem 1B, we sort of adapted the way that we thought about our chemical reactions as being able to go in both directions here. All right? What can we say about the reverse direction here relative to the forward direction, specifically looking at those activation energies? Which one is going to be slower? The forward direction or the reverse direction? In the forward direction, my activation energy barrier is this whole thing here, this big hump. If I'm in the reverse direction here, I'm starting out on my product side, then my activation energy barrier is only this big. All right, so for our endergonic reactions here, All right, your reaction is slower, larger activation energy in the forward and faster in the reverse direction. All right, kind of all these are saying the same thing. Endergonic, reactions slower in the forward than the reverse direction, right? These are reactions that will favor the reactant side. All right, if we just kind of want to go back up and complete here for our exergonic, these have a negative delta G, meaning our products are lower energy than our reactants. All right, these are reactions that favor the products. And thinking about it again from a kinetic standpoint here, which one of these reactions would be faster? Going in the forward direction or going in the reverse direction? Going in the forward direction. If we're going in the reverse direction, now we have to overcome this entire barrier here. Okay, cool. So important things that we're going to think about. One last thing that I'm going to note is up here at the top of this activation energy barrier, the tippy top point here. We have a special name for this. We call this our transition state. It is the highest energy state in your reaction here. All right, your transition state is when you have your half-broken, half-formed chemical bonds. Right, so it's that point right in the middle where your old bonds are breaking and your new bonds are trying to form. All right, that's what we call our transition state. It is the highest energy state in our little diagram here. Cool. We're going to be using these diagrams to talk about these different substitution and elimination reactions. All right, so what do I mean by that? So again, today's topic of discussion is going to be substitution. And there's two different types of substitution reactions that we're going to see. They're very similar, all right? But what we call SN2 versus SN1 reactions. All right, so what is an SN2 reaction? So the S stands for substitution, the N for nucleophilic. So these are nucleophilic substitution reactions. All right, I sort of already prefaced that at the beginning by demonstrating that our substitution reactions happen when we react our alkyl halides with a nucleophile. Right, so these are what we call nucleophilic substitution reactions. If we look down here, this is also an SN reaction. So these are also nucleophilic substitution reactions. The difference is obviously in this number at the end. 2 versus 1. All right, so what's the difference here? An SN2 reaction, the 2 is because it's a bimolecular reaction. Okay, we talked about this unimolecular, bimolecular, termolecular. This was back in Chem 1B when we were discussing kinetics. All right, so a bimolecular reaction tells you about the kinetics of that reaction. And remember, our kinetics of our reaction are determined by the rate limiting step in our mechanism. Whatever that slowest step is in our reaction mechanism, that's what corresponds to our kinetics. So they often use kinetics as a way to kind of establish what a mechanism is. So a bimolecular reaction is because our rate depends on both the concentration of nucleophile and alkyl halide. All right, both the alkyl halide and the nucleophile are involved in the rate limiting step. All right, so taking us all the way back to Chem 1B here, if I wanted to do my rate law for a SN2 reaction, that would be rate is equal to some constant K times the concentration of alkyl halide times the concentration of nucleophile. All right, an SN1 reaction is also a nucleophilic substitution reaction, but it's got different kinetics. It is a unimolecular reaction. All right, SN1, there's only one of those involved in that rate determining step. Our rate depends only on the concentration of our alkyl halide. The nucleophile is there, don't get me wrong, the nucleophile is essential for the reaction to occur, but it's only the alkyl halide that is involved in the rate limiting step. Say only compound in rate limiting step. What's up? Yeah.
Yeah, it's all wrong.
Yeah, it's all nonsense.
Yeah, I don't know what's going on.
I punched a whole bunch of just
Same
DCM
thing over and
runs.
over again?
Yeah, just DCM.
Okay.
And the first one was a mess,
Yeah.
and they're still not great after
Still
that.
not, yeah.
Yeah.
Okay.
I don't know, we'll have to mess with it.
Yeah.
Okay. Unimolecular only depends on that concentration of our alkyl halides. So again, if we were going to do our rate law, that rate is equal to some constant K, but now only times the concentration of that alkyl halide. All right, so we got these substitution reactions that we're going to discuss, and we're lumping them into these two camps here. Either reactions that are SN2 reactions, they have this both alkyl halide and nucleophile in the rate limiting step, or SN1 reactions, only the alkyl halide in that rate limiting step. All right, so let's take these one by one then. Let's first look at our SN2 reactions. All right, and the key to understanding the differences between these two, really they correspond to different mechanisms, right? We're talking about, the names, the 1 and the 2 come from the kinetics, but we're talking about the rate limiting step in their mechanisms. So that's what the big difference is going to be, is how we draw our electron pushing arrows for SN1 versus SN2. So let's look at our reaction mechanism. All right, we got our alkyl halide. We're going to react this with some nucleophile. Again, I'm just going to use generic Nu for right now. All right, importantly, both of these are going to be involved in this rate limiting step here. So my nucleophile attacks that electrophilic carbon and kicks off that leaving group all in one shot. All right, so our nucleophilic attack and our leaving group leaves all in one step. All right, and I guess if we're going to be good, we also have that leaving group, that bromide ion that's kicked off as well. Okay? So this is what an SN2 reaction is, kind of the simplest way that you would think about a substitution reaction. Your nucleophile attacks and your leaving group leaves, and that happens all in one step. All right? Both the nucleophile and the alkyl halide are involved in that step, which is why it gets the 2 for being a bimolecular reaction. All right, now let's put this and look at our energy diagram here. All right, what I'm going to do is I'm going to sketch out one of these reactions up top, and then we're going to draw the corresponding steps down at the bottom, or rather the diagram energy levels down at the bottom. And I'm going to draw the geometry. I'm just going to use a very simple bromomethane, just a single carbon alkyl halide here. But I am going to draw my tetrahedral geometry correctly. So since I have these 2 bonds in the plane of the page, that means I need 1 hydrogen sticking out at me and another one pointed into the board. All right, so now we're going to, underneath here, we're going to sketch out our energy diagram. And these are my reactants. So I'm going to start out at this energy level here. All right, my nucleophile is going to attack, and my leaving group is going to leave. And when this happens, that's when we get this increase in our energy diagram. And what do we say lives at the top of that energy diagram, that hump? What do we call that local maxima? That transition state. All right, so let's sketch out our transition state for this SN2 reaction here. All right, this is not technically part of our mechanism, but we are going to look at what this looks like. Your transition state is not something that you can like isolate. It exists, it is the highest energy point on this graph. So it's quickly going to fall in one direction or the other down this energy hill here. But nonetheless, the transition state can give you a lot of information about your reaction. All right, and again, what we would see is we have our carbon. It's got this nucleophile on one side and this halogen on the other side. And these bonds are in this half-broken, half-formed state. All right, so I'm going to use these dotted lines here to indicate these bonds are half-broken, half-formed. Okay, and then this graph is, once it reaches that transition state, it's going to crash downhill here until we get to our product energy level. All right, now importantly, when I did my transition state, I kind of conveniently left off those hydrogens. All right, what we're going to see is this transition state here. It is no longer a tetrahedral geometry. It instead adopts this planar geometry. All right, these bonds here are now all in the same plane. It's flat. Which means that when we get to the other side here, we have our nucleophile carbon bond. Our hydrogens, all three of them used to be pointing off of here to the left, away from that leaving group. Now what we're going to see is they're all pointed to the right, away from that nucleophile. Okay, so my nucleophile here, because it must attack from the opposite side of where that leaving group is, right? Your nucleophile can't attack from over here. It's got that leaving group in the way. It has to attack from the opposite side, what we call our backside attack. That leads to our planar geometry of our transition state, which will lead to a stereochemical inversion. All right, I guess I'm going to be good and label this axis here. These are my reaction coordinates. All right, now in the case of bromomethane, it doesn't really matter because there isn't a stereocenter there, but let's use a stereospecific alkyl halide. All right, so this is our stereospecificity of an SN2 reaction. All right, I've been using generic nucleophile up until this point. Let's do a specific nucleophile here. the hydroxide ion. How can I tell that hydroxide's a good nucleophile? It's got the charge, the negative charge, right? Nucleophiles are those electron-rich species. All right, and if we wanted to go back and remind ourselves, everybody take a second and assign this stereocenter as being either R or S. There should be a negative sign. I don't know what happened to it. All right, my bromine's 1, this carbon's 2, this one's 3, so we're going in this clockwise direction, which makes this the R stereochemistry. All right, and what's going to happen when my hydroxide attacks from the back side here, kicking off that leaving group? That means my new bond is going to be pointed into the page. All right, and we can convince ourselves that we had this stereochemical inversion where that stereocenter flipped from being R to S. All right, so our SN2 reactions have what is called a stereochemical inversion. About that chiral center that's getting attacked, about that electrophilic carbon, we flip our wedged bond of our leaving group to a dashed bond of our nucleophile, right? Our new bond is forming in the opposite direction of where our leaving group was. Cool. So that is our SN2 reaction. All right, it's called a SN2 because it's a bimolecular reaction in terms of the kinetics. Both the alkyl halide and the nucleophile are involved in that rate limiting step. All right, maybe we just want to note here, this had that one step mechanism. Nucleophile attacks, leaving group leaves all in one shot. New bonds formed, old bonds broken, all in the same step. Cool. So this is going to distinguish us from our SN1 reactions. Again, to better understand these SN1 reactions, we got to look at our reaction mechanism. All right, so here's an alkyl halide. We're going to add in generic nucleophile here. Everybody take a second. Before we even do our mechanism, just draw me what my product should look like here. We're going to swap out that nucleophile. Swap out that halogen for our nucleophile. All right, our nucleophile is negatively charged. Let's just note here, just like we saw over here, what happens to that extra lone pair? It becomes that new carbon nucleophile bond. So that's why my nucleophile goes from being negatively charged with a pair of electrons. That pair of electrons now lives in that carbon nucleophile bond. All right, but if I'm going to do my mechanism here, this first step is our rate limiting step. So are both my alkyl halide and my nucleophile going to be involved? No, only the alkyl halide is involved in this first step. And what happens is that leaving group just kind of falls off. All right, we have a special name for this intermediate that's formed. What's it called? What am I missing over? So if I do my charge conservation, this got kicked off as a bromide ion. So what am I missing? A positive charge. And where's that positive charge going to go? On that carbocation, this carbon right here. All right, let's just convince ourselves that carbon was perfectly happy over here with its complete octet, and we stole this pair of electrons from it, leaving us with an incomplete octet, our carbocation. All right, now our nucleophile will be involved in this reaction here. Our nucleophiles, carbocations, are great electrophiles. They're good at accepting pairs of electrons. Let me move this over. So our nucleophile is going to attack that positively charged carbon, and that's how I get my new carbon nucleophile bond. So this did not occur in this one step where we broke and formed all our bonds like we did in SN2 reaction. Instead, first we have that leaving group leave. And then in a second step, we have that nucleophilic attack. All right, so now let's do the same thing that we did before, where we're going to do our energy diagram. All right, so we're going to start our energy diagram with our reactants here. Our bromine and our nucleophile. All right, so starting at our energy level here for our reactants. And then again, that first step is that leaving group leaves, forming our carbocation intermediate. Actually, it's a different color. All right, now there's kind of a subtle difference between an intermediate and a transition state here. All right, notice how I didn't put brackets around this. I didn't call it a transition state. I called it an intermediate. And we can illustrate that using our energy diagram here. We go up, we go through a transition state, and then we hit this local minimum here. And this is where my intermediates live. All right, is this intermediate lower or higher energy than my reactants? higher energy. And yes, that's because carbocations, not very stable. They do not have complete octets. But importantly, this isn't a transition state that lives in one of those local maxima. This is an intermediate, which means that it is this local minima. All right, it's this little dip in our free energy diagram. Okay, then my nucleophile will attack that carbocation, leading me to my products. Okay. So our SN2 mechanisms. The mechanism itself is just one step. Nucleophile attacks, leaving group leaves all in one shot. And that's reflected in our reaction, our energy diagram, because we just got that one hump in our energy diagram. In an SN1 reaction, we have this two-step mechanism. Our leaving group leaves, and then our nucleophile attacks that carbocation intermediate. We can see these two steps in our energy diagram as well, because we go up through our first transition state, then we're down at this intermediate, and then up through a second transition state before we get to our product side. All right, so just note, we do still have transition states. This would be transition state 1. This one would be transition state 2. These are, again, when our bonds are half broken in the case of the carbon-bromine bond, or half formed in the case of the carbon nucleophile bond. All right, and then, of course, on either end, we have our reactant energy and our product energy. All right, so our SN1 reactions, all right, these are unimolecular. That rate limiting step in my mechanism depends only on my alkyl halide. All right, let's just note that our mechanisms here have these carbocation intermediates. All right, last thing before we move on here. If we do this first step in our mechanism, going from our reactants over to our products, all right, what could we say about the rate of this forward versus reverse reaction here? Which one's going to be faster, going forward from reactant to intermediate, or going backward from intermediate to reactant? Going backwards. So for being good in our mechanisms, and I told you I didn't care about this when we were doing our mechanisms before, but for these we're going to be good. And we're going to show that this first step here is indeed a reversible step here, meaning that it goes back and forth in both directions until you jump over this way and get stuck on the product side. So in our mechanisms, let's go back and update our arrows here to be these two-headed arrows to show that these reactions go in both directions. That first step specifically goes in both directions. After we go from intermediate to product, now it would require a lot more energy to go back in the reverse direction. All right, but when we do that first step here, we can sort of go back and forth. Okay, one more thing with regard to SN1 mechanisms. Because they do have carbocation intermediates, carbocations are just about the best electrophiles that you could have because they have that net positive charge and they have an incomplete octet. They're really good at accepting electrons. So you can actually get away with using crappier nucleophiles. All right, so what we're going to see for our SN1 reactions is we can use these neutral nucleophiles. So let's take an alkyl halide here. I'm going to tell you it's an SN1. We haven't even gotten to like how I can tell SN1 versus SN2. We'll talk about that here in a second. All right, but I'm going to tell you that this is an SN1 reaction where our nucleophile is not going to be that strong nucleophile hydroxide, but rather this weak nucleophile of just water, right? I can tell it's weaker because it's neutral. Okay. We're going to do this first step in our mechanism. All right, what happens in that first step? If it's SN1, leaving group leaves. All right, so now this is the step where our nucleophile is going to be involved, that water. In my carbocation, that electrophilic site is obviously that positively charged carbon. Hopefully that's a no-brainer. All right, but where's that nucleophilic site in water? Not the hydrogen, because what does a nucleophile need? Electrons, right? So my oxygen and its lone pair are going to be my nucleophile. Boom. So then everybody take a second. Give me the product of this step here. All right, was that a bond formation or a bond breaking arrow? Bond formation, so I have this new carbon-oxygen bond here, but I still have those two hydrogens on that oxygen atom. So complete this intermediate for me. What am I missing? I got lone pair, and then what should my charge be? Positive charge. All right, and this isn't going to be our product of this reaction. We're going to have a neutral product. So there's going to be one more step here where we're going to deprotonate that oxygen. We got bromide floating around, and we got water floating around. We're going to be good and use, first of all, there's a lot more water present than there is bromide ions, but water is also the stronger base of the two. So our water is going to deprotonate that oxygen, leaving us with an alcohol functional group. Devil's in the details on to your concentration, but no, we're going to say that this is just a straightforward from here. All right, so the bottom line is, look at my nucleophile compared to what was actually attached to my molecule. I had two hydrogens over here on my neutral nucleophile, but only one when it formed this bond. So we're going to make a note that our neutral nucleophiles lose a hydrogen when they react. All right, and last thing we got to discuss with our SN1 reactions are stereospecificity of those SN1 reactions. All right, so previously I was using an example that was not stereospecific. So let's look at an example that is stereospecific. All right, we're going to react this with some nucleophile here. But importantly, that first step is kicking off that leaving group. All right, and when we form that carbocation intermediate, we've talked about carbocation intermediates and their stereospecificity. That carbocation intermediate does not have that same tetrahedral geometry. It is instead a trigonal planar geometry. Which means that my nucleophile will 50% of the time attack from one side and the other 50% of the time attack from the other side, giving us a racemic mixture. And when we do our racemic mixtures, we don't show our stereospecificity with dashed and wedged bonds. Right? So we would just use these straight line bonds here. Whoops, not 3R, but nucleophile. All right, and what we've shown here is our nucleophile attacks that carbocations from both sides, leaving you with a racemic mixture as your product. All right, and we saw this with carbocation mechanisms before. All right, just like our other ones, our SN1 reactions go through these carbocation intermediates. So the stereospecificity, we can just note we lose our stereospecificity, lose our stereochem in our reaction. Meaning that even if we started out with a stereospecific reactant, all right, this is the S reactant here, we're going to get a racemic mixture of both possible products, which we represent with our straight line bonds. Okay, so now last thing we have to discuss are which of our alkyl halides undergo SN1 versus SN2 reactions. All right, so the key difference here between these two mechanisms is one of them has a carbocation intermediate, the other one doesn't. And we talked about carbocation stability. And that has to do with what? What makes a more stable carbocation? Tertiary versus a more stable than secondary, than primary. What we called our degree of substitution, right? So if we're going to rank these from least to most stable, The least stable would be a carbon that doesn't have any other carbon neighbors, a methyl carbon. All right, a little bit more stable than that is a primary carbon. A little more stable than that is a secondary carbon. And then we have our tertiary carbons, which up until now were our most stable carbocations. But there's one more that we're going to add to this list here. And that is when that carbocation is sitting right next door to a pi bond. What do we call that position? The allylic position. All right, so methyl, less stable than primary, less stable than secondary, then tertiary, and then lastly now we have these allylic carbocations that are even more stable. All right, and what we're going to find are these less stable carbocations. These would be compounds that then don't form carbocations. They go through SN2 type mechanisms, whereas these compounds here that form our nice stable carbocations, these will undergo SN1 mechanisms. All right, so SN2 will be for methyl primary or secondary alkyl halides, whereas SN1 will be for tertiary and allylic alkyl halides. Cool. All right, so then what I could ask you to do here is give me my substitution products. We got a bunch of different alkyl halides here. I'm actually going to put one example using that tosyl group. All right, so why doesn't everybody take a second, copy these down, and start working on them? I want you to work on these before next class period. This is where we're going to pick up with next class period. Cool. All right, so yeah, I'm gonna leave this up here. Take a second to copy this down. This is where we will pick up next class period. I want you to try to work on these at home. Try to predict your substitution products. Be stereospecific when you need to. You want to think about which one of these two mechanisms, SN1 or SN2, these specific substrates will undergo in order to be able to predict what their products would be.